Welcome back to K.S.R Concepts of Chemistry. Today we are discussing metamerism, ring chain isomerism and some problems related to IIT, mains and NEET. Okay. So what is metamerism? Compounds having same molecular formula. And same functional group. The functional group must be multivalent functional group. Multivalent means either bivalent or trivalent functional group. Okay. But difference in the alkyl groups attached to the function. Alkyl groups attached to the function. Those are known as metamers, and the phenomenon is known as metamerism. We are discussing some examples. That is, number one example is methyl propyl ether. And another example is diethyl ether. So both are having same molecular formula and same function. The molecular formula is a C4H10O. Both are having same molecular formula, same functional group. But difference in the alkyl groups attached to the function. Here methyl, this is propyl. This is ethyl and this is ethyl. So difference in the alkyl groups attached to the functional group. These are known as metamers. And so another example also you can take, that is methyl propyl thioether and diethyl thioether. So in these are having same molecular formula, that is C4H10S and same functional group, that is thioether, but difference in the alkyl groups attached to the functional group. That is methyl, this is propyl, this is ethyl, this is ethyl. Now left side alkyl groups are different, right side also alkyl groups are different. On both sides alkyl groups should be different to exhibit metamerism. So these are metamers. To exhibit metamerism, there is some important point is there. Multivalent functional groups only exhibit metamerism. Multivalent functional groups only exhibit metamerism. For example, thioether will exhibit metamerism, and ether will exhibit metamerism, and secondary amines will exhibit metamerism. Tertiary amines, that is trivalent functional group, this is divalent functional group. Divalent and trivalent functional groups will exhibit metamerism, that is tertiary amine we can take. And we can take ester, this is the divalent ester, and thioester, and ketones will exhibit metamerism. Thioketones will exhibit metamerism. Alage the groups, the functional group like this type of functional groups also exhibit metamerism. So all these, that is trivalent or divalent functional groups, will exhibit metamerism. Okay. Now we are discussing some examples and some questions on this. We can discuss some questions on this. That is question number one. This is phenyl ring. This is carbon ring. This is oxygen, cyclohexyl group is there. And another one cyclohexyl group. This is carbon, oxygen, phenyl group is there. Question number 1. And question number 2. methyl ketone we are taking. This is methyl propyl ketone. Methyl propyl ketone we are taking. This is question number 2. And question number 3 is C double bond O. Yes, methyl. This is S. This is ethyl. And C double bond O. Yes, this is methyl. Yes, this is ethyl. Okay. So we have to find out whether these isomers metamers or not. Here carbonyl group is attached to the phenyl. Here carbonyl group is attached to the cyclohexane. Here oxygen is attached to the cyclohexane. Here oxygen is attached to the phenyl. So alkyl groups on both sides are different, and same molecular formula and same function group, that is divalent function group. Ester. Ester is the divalent function group. Same function group, same molecular formula, but alkyl groups on both sides are different. So these are considered as metamers. And if you take this ketone, here ethyl group is there, here ethyl group is there, here methyl group is there, here propyl group is there. So here alkyl groups attached to the same function group are different. Function group is same, molecular formula is same. Alkyl groups attached to the same function group are different. On left side alkyl groups are different, right side also alkyl groups are different. So these are considered as metamers. If you take these molecules, here C double bond O, yes, S, C double bond O, yes, S. So here function group is same. Function group is same, no doubt. Molecular formula is same, because here methyl group is there, here methyl group is there, here methyl group, and here methyl group is there. Molecular formula is same. But here sulfur is attached to the ethyl. Here also sulfur is attached to the ethyl one side. And the other side sulfur is attached to the methyl, the other side sulfur is attached to the methyl. So same alkyl groups present on both sides. So these are not considered as metamers. These are identical compounds. These are identical compounds. Okay. So we can discuss some other examples. Next example is C double bond S. This is CH3. This is H. This is H. This is C double bond O. OPH. OPH. So next one, C double bond O. This is PH. This is C. This is H. This is C double bond C. This is CH3. This is hydrogen. So consider these molecules. This is the ester bivalent function group. Ester bivalent function group. Here carbonyl group is attached to the alkene. Here carbonyl group is attached to the phenol. Here oxygen is attached to the phenol. Here oxygen is attached to the alkene. So difference in the alkyl groups on right side, on left side. So these are considered as metamers, and these are having same molecular formula also, same function group also. Okay. So next question number 5. Question number 5 is we can discuss question number 5 like this. That is phenylene is there, methyl group is there, here ketonic group is there, here cyclohexyl group is there. Okay. So in the next molecule, cyclohexyl group, methyl is there, and here C double bond O, C double bond O. This is phenyl group is there. Here both are having ketonic group, same function group, same molecular formula both are having. But here toluene group, this is toluene group, and here cyclohexyl group, and here toluene. This is methyl cyclohexyl group. This is phenylene. So alkyl groups on right side toluene here methyl cyclohexyl. So left side is toluene, here methyl cyclohexyl, right side is cyclohexyl here, this is phenyl here. So alkyl groups on both sides are different. So these are considered as metamers. Okay. We can discuss the other example that is CH3, CH2, CH2, propyl methyl amine, compound A, and compound B is diethylamine, that is compound B, compound B is diethylamine, and compound C is isopropyl methylamine, compound C, and compound D is like this, ethyl N-dimethylamine. So like this we are taking compounds. So these are all having same molecular formula, and these are all isomers, no doubt. If you consider A and B, so these are having same molecular formula, that is C4H10N, C4H11N, same molecular formula, and same functional group secondary amine, but alkyl groups attached to the functional group. This is propyl on left side, this is ethyl on left side, this is methyl on right side, this is ethyl on right side. So alkyl groups attached to the functional group are different. So these are considered as metamers. If you consider A and C, that is here right side is methyl. In this compound also right side is methyl. So here alkyl groups are same on one side. At least one side alkyl groups are same. So that's why these are not metamers. Here NHCl3 is considered as substituent, and the parent chain is this is propyl. Propane is the parent chain. Here 1, 2, 3. Okay, the substituent is at second position for this parent chain. Here the parent chain is propane. Here NHCl3, ethylamine is the substituent. The substituent is present at first position. Here substituent is present at second position. So these are considered as position isomers, not the metamers, because one side alkyl group is same. So these are considered as position isomers, not the metamers, because position of the substituent is different. Here second position, substituent is at second position. Here substituent is at first position. Next one, if you take A and D, so this is the secondary amine, this is the tertiary amine. So in these compounds, functional group is different. To exhibit metamerism, main important condition is functional group should be same, but here functional group is different. So these are considered as functional isomers. And B and C, if you observe B and C compounds, this is the secondary amine, this is also secondary amine, and here right side is, so left side is propyl group is there, isopropyl. Here left side is ethyl is there, right side methyl, here right side ethyl is there. So these are considered as metamers, because on both sides alkyl groups are different. So these are considered as metamers, B and C. And B and D, if you taking B and D. So in the case of second one is secondary amine, and D is the tertiary amine. So functional group is different. These are considered as functional isomers. And if you take C and D, so this is the secondary amine, this is the tertiary amine. So these are also considered as functional isomers. In this way we can identify functional isomerism or metamerism, positional isomerism like this. And another example we can discuss now. This is the most important example. CH3O, CH2, CH3, and another one is CH3O, CH3. So in this left side alkyl group is same, both are methyl. Okay, so these are not considered as metamers, even though functional group is same, molecular formula is same. Left side alkyl groups are same, so that's why we are not considered as functional metamers. Here the parent chain is propane. This is 1-methoxypropane. Here parent chain is the longest chain, and numbering is given like this, 2-methoxypropane. So these are considered as positional isomers, but not metamers. The question is there, that is so this is the ether given. 1, 2, 3, 4. Okay. So another ether given like this. This is not ether. Actually, this is epoxide. This is epoxide. So we have to identify these isomers. This is actually epoxide. This is the this is also epoxide. This is also epoxide. Here 1,4 epoxy butane. Epoxy butane. Here 1, 2, 3, 4. 2, 3 epoxy butane. 2, 3 epoxy butane. So both are having same molecular formula, but the position of the functional group is different. Position of the functional group is different. So these are considered as position isomers, not the metamers. Not the metamers. If you take a molecule like this, cyclohexane and methyl cyclobutane, both are having same molecular formula, and both are cyclic compounds, ring compounds. And here XY is isomeric number is that is 60. Here isomeric number is 5, 1. That is number of carbons in main chain is 5 and substitution is 1. So 5, 1. So isomeric number is different. These are considered as chain isomers. Chain isomers. Okay. So these are very, very important questions. Now we are discussing ring chain isomer. Ring chain isomer. Here compounds having same molecular formula, and one compound is cyclic compound. So another compound is open chain compound. Open chain compound. So these are having same molecular formula, that is C4H. But one is cyclic compound, another one is open chain compound. This type of isomers are known as ring chain isomers. Ring chain isomers. Here for C4H8, degree of unsaturation equal to half into 2 into carbons plus 2 minus M plus T. This is the formula to calculate degree of unsaturation. C is nothing but number of carbon atoms, M is nothing but number of monovalent groups, and T is nothing but number of trivalent groups. Okay. So for this C4H8, degree of unsaturation is half into 2 into number of carbons is 4 plus 2 minus monovalent atoms is 8. There is no trivalent atoms. Here hydrogens are monovalent atoms because they are forming single bonds. This is 8 minus 8 cancel. This is 1. This is 1. Degree of unsaturation is 1. That is, there is one multiple bond. One pi bond is there. So that is cyclobutane or but1ene. So these are ring chain isomers. So next one, ring chain isomers. Example is cyclohexane, and we can take N-hexene, hexane, N-hexene. So these are ring chain isomers because these are having same molecular formula. This is 6, so H12. One is cyclic compound, another one is open chain compound. So these are ring chain isomers. Okay. So next one we can discuss some questions on this. That is, number 1 is C4H10. Calculate the number of structural isomers. For C4H8, degree of unsaturation is half into 2 into 4 plus 2 minus 10. This is 8 plus 2, 10 minus 10, 0. Degree of unsaturation is 0. There is no pi bond here. So we can take butane like this, and we can write isobutane. So these are the chain isomers. We can't write position isomers because there is no substitution, there is no functional, there is no multiple bond. We can't write positional isomers, only chain isomers. That is 2 is possible for C4H10. and C5H12. Next question is C5H12. C5H12 degree of unsaturation is so half into 2 into 5 plus 2 minus 12. This is 0. This is 0. Degree of unsaturation is 0. So n pentane you can take, and we can take isopentane we can take, and we can take neopentane also we can take. These are the chain isomers. Totally 3 possibilities are there. 3 structural isomers are possible. There is no position isomers, there is no functional group isomers, because there is no functional group, there is no substrate. Okay.